I mean, sepsis kills 5 million people a year. Basically, one person every 7 seconds dies from sepsis. It's probably the biggest killer, and it's certainly the major pathway to death for individuals that have an infection worldwide. So detecting or identifying sepsis is really challenging, simply because the symptoms are pretty nondescript. They could be just simply a temperature or not having a temperature, just feeling low in energy. And so what can happen is that sepsis can go undetected. By the time you now start to develop very serious signs from sepsis, it's likely to be too late, and there's a very high risk of dying. So there is an urgent, unmet clinical need in the clinical setting for being able to have a reliable way for detecting sepsis. The way to think about that is around how the immune system actually evolves as you go forward in time with a history of events in terms of infection, vaccination. And so by studying and understanding, if you like, the newborn baby, which hasn't had that history, the immune system is relatively clean, almost like a blank slate. So we're able to pick up, if you like, very strong signals that happen early in life that then can translate for us as in the older populations, so into children and adults. So part of the research that we're doing is to try to meet that unmet need of detecting very early on sepsis, and how and by early detection you can get more effective treatment. Now, in that process of understanding the basic science that goes on, which involves crossing many different disciplines, from mathematics to biology to medicine itself on the clinical side, we're able to actually see what's happening mechanistically in patients that are actually showing signs of sepsis. And those insights are providing ways that we might think about intervening and trying to reverse those steps. And so to do that is a highly multidisciplinary team involving not only the clinicians but also the public and the patients themselves in what we're doing.